Today I'll be talking about DragonKit. Why it's called DragonKit? I named it because most of the stuff related to LLVM contains, well, the logo of LLVM contains dragon, and the reason behind that is that the famous book was containing also a dragon on the this will be, I'll be presenting some work I've done on providing a compiler framework natively in OCaml. Hopefully it can be generic. So what are the reasons? We love LLVM, I think. We praise GCC, but we admire quick C minus minus aircraft of MRVs, because these frameworks are not that well known in the industry, but they have many, in many ways they are kind of different, and majority of the industrial strength frameworks, LLVM or GCC, are tailored for compiling imperative languages like C++, C, Objective-C, and so on. So the idea was to provide something that can compile all the languages, not only that, but focusing on functional language, of course. So do we need another compiler framework? I don't know. So the language development is a really huge topic in academia, in the industry. There are lots of languages. Supporting them is very difficult. Supporting them in the compiler is really difficult. And having a compiler framework fixes that problem, that we need to ensure that the compiler is generic. So we know a lot about language, about computer languages. There's lots of research going on, but there is language barrier because they are different. It means that most of them don't have huge denominator and not much opportunity to do in the compiler framework the domain-specific optimizations. And so much needs to be done anyway in the front end. So what I will present here, well, I attempted to think about all these problems. I even tried at some point to experiment LLVM, and I thought that implementing a backend would be a good idea, because IR is very well known, but backends are not known. I'll talk about this later. So I started with thinking about how to represent the backend, because that's the hardest part, I think, because backend could be, majority of backend stuff could be generated out of some clear specification, because that's what I think. Looking at the LLVM backends, there's lots of redundancy. So I will also talk about a little bit about needing, because of course I needed to compile something to actually verify if my solution works. That's not too much, but I think it proves some of the concepts that are valid. And I will tell also about general plan. So it's quite far to release that stuff, but I think people might look at the GitHub. Not everything is yet there, and the DragonKit is just a component that works on top of some other parts. I can't talk about everything what I discovered, but of course, the 15-minute presentation has obvious implication that I need to kind of use shortcuts. Yeah, I said a backend is paying to develop, because architectures, almost every architecture, something crazy about this. For instance, ARM has IT blocks and conditional instructions. MIPS has some other restrictions which I don't know about, but I heard that it has x86. Everybody knows what is x86 and how to deal with that, like variable length encodings. So actually, I give a shot and tried LLVM backends to develop LLVM backends from scratch. And here are the results. Developing LLVM backend, but not a language backend for LLVM, means that a backend for an architecture like some virtual machine or something similar is is more difficult than developing a backend for a language based on LLVM that compiles to IR. There are lots of unknowns. The biggest challenge is the easiest way of doing that is to just copy existing backend, which is similar to the backend, to the DragonKit backend, and then tries to adjust it. But there's still lots of C++, custom C++ that it's not easy to comprehend what's going on. Although I think LLVM has nice C++ code base. I believe it's one of the nicest C++ around. But there are other problems maintaining that because, for instance, building a client frontend takes about 10 minutes and takes 4 gigabytes to debug symbols of memory, which is not feasible. Because my machine might have just 4 gigabytes and will start swapping. So Arch, what is Arch? Arch is backend description language. Currently it does just 2 things, but I'm thinking about extending that. Instruction encoding description, instruction syntax, and assembly pretty printing, and code generating in progress, but I know specified, I still need to kind of construct this code. But it does type inference and type checking on top of that. So, for instance, it checks for the size of bit fields. If you concatenate 2 bit fields, it will result in. So there's lots of things that can happen statically because basically one is generating the code out of it. So these things are known. So these features are planned currently. So I won't talk about them, but instruction selection like LLVM does, instruction parsing, so we can kind of have reverse transform of that. So how the Arch and TableGen is different. So TableGen is a language for structuring and collecting the data and feeding up to the backend. So it's very generic language. It's actually a sophisticated macro language with kind of DSL twist, like you can specify how the instructions will be selected, and you can specify the assembly syntax, but also you can generate inline some C++ code inside as well. So in Arch, I took different approach. Arch is effectively rich and specialized. Arch just generates uniform code, and Arch generated code will always compile. So it doesn't contain any explicit ML in it. I hope that I will not need to add any quotations to it, but might be tend to be not possible. So type system. So we have this big data type and performs a lot of static checks, like for instance alignment of the bit fields, very simple check, like all the stuff that might be not obvious and might be error. I discovered at some point that actually these languages are similar in spirit to Boomerang. Means that there's always a reverse transform from one to another. And this is interesting property. I'll talk about this later. So what is TableGen good at? I think it's very good for kind of structuring the data. It's very generic and it's simple, just 5 lines of C++, which is amazing for me. I thought about Arch and I thought that DSL, developing DSL is quite cheap. I found that pattern matching is the major part in backend. I wanted to generate all the tools. I wanted to support different backends, maybe TableGen backends. So they serve the same purpose, and do it well, I think. Example. So first, we've got definition of the Arch prelude, which is actually very similar to what MLRISC does, because it has similar language. And I actually took a bit of ideas from that, and so we have all these attributes of the architecture. We define a register bank. We define the behavior of that, aliasing information that backend can be used. Because these things are generic, so they should be part of the language. So type definitions. Type definitions are really polymorphic variants. because of polymorphic variants, I could exploit sharing, and that was the major reason. And they kind of compatible with the type system of ML. I don't know how it would look like in C++ though. Tables combine. I need to be fast now. So there are also type predicates, which I can structure the data. This is how the definition looks like. So this was complicated case. This is simple case, kind of, and this is the simplest case. Leave instructions is just fixing the stack frame before. So most of the stuff is happening on the types. Interesting that this is a generated code, and I'm using carry to 4 for that. And I'm very happy that I can use quotations. This is instruction definitions. This is actually the code which deals with emitting the bits. And you see, all the stuff was reduced to numbers. We don't need to kind of, because of optimization, it performs. And as I said, I'm very happy that quotations exist. So I tried to develop a simple JIT for that. I was aiming to generate the backend, of course, without touchable cable, but that might be not possible later. So I had SSA form, I have coloring, register coloring, simple algorithms for coloring registers, for register allocations. I have LLVM bridge. I have all the Arch generated boilerplate. So the exercise was to port the LLVM example. And I succeeded. I also extended the example. And I could run the example in REPL. And we have a compiler. So that's how the code generation looks like. It's Monadic interface for generating the SSA form. So all these things are due to, it should be really a tree, but I decided to go for SSA test. And then use the TableGen. So it worked. That's how the language looked like, and that's how it looked like before, after constant folding, after graph coloring. Don't try to analyze it, because I'm sure it's wrong, because I took this some time ago. It also generates dot graphs. Yeah. So
you need to complete that.
yeah. So okay. So maybe it's wrong slide. I don't know. So basically, I use my spare time to do this, and this is an interesting experiment, and I think people might be interested in contributing. Then feel free to contact me and anybody wants to. But it's hard to contribute, I admit, because it's not well specified yet. Maybe next year on OUD. Okay, questions.